Hello Calc 3, welcome back to another video. In this video we'll be talking about section 14.4 which addresses the chain rule for functions of several variables. So remember that back in Calculus 1 we developed a formula that gave us the derivative of the composition of two functions. So what exactly do I mean by that? Well, if we have a function w equals f of x and that function is differentiable, and we also have that x is a differentiable function in the variable t, so that x is equal to g of t for some g of t. Then we can take the derivative of w with respect to the variable t, and we find that that derivative is equal to the derivative of w with respect to x, multiplied by the derivative of x with respect to t. And we call this the chain rule for single variable functions. So when this is the case, we can write w as a function of t by saying that w of t is equal to f of g of t, and we can think of t as an independent variable and x as an intermediate variable, because t is going to determine the value of x completely, and then x is going to determine the value of w completely. So t ultimately determines the value of w completely when this is the case. And for functions of several variables, the chain rule has multiple forms, and these different forms are going to depend on the number of intermediate and independent variables that are associated with our particular function. So with that being said, let's move into the case where we have functions of two variables. And we'll start off with a theorem. So if w is equal to f of xy is some differentiable function, and if x is equal to x of t and y is equal to y of t are differentiable functions of t, then w is equal to f of x of t, y of t is a differentiable function of t, and we can talk about the derivative of w with respect to t, and we find that that derivative is going to be equal to partial f with respect to x times the derivative of x with respect to t plus partial f with respect to y times the derivative of y with respect to t. So again, here we have a function in two variables, and then each of those two variables can be written as a function in the same variable t, where t is going to be the independent variable here, and x and y are both intermediate variables. And in this case, you can see that the chain rule is more complex here than it is for single variable functions. And a proof of this theorem is given in the textbook, but I don't want to cover it just because it's long, and this video is going to be long enough without adding that proof. So let's just skip over it. If you are interested, then you can always go into the book and look for the proof. And just a quick remark before we keep moving on here. We could also rewrite the expression for the derivative of w with respect to t as partial w partial x times the derivative of x with respect to d plus partial w with respect to y times the derivative of y with respect to t. So here we're switching f and w. So we can use either notation there. So we will often use what are called branch diagrams to remember our various chain rules. We're going to be going through a bunch of different chain rules in this video, depending on the type of function that we're working with how many variables the function is in, and then how many, or how we're going to express those variables as functions of other variables as well. And it's going to change what the chain rule looks like. So these branch diagrams are a way to remember what the chain rules are going to be and hopefully develop them when we don't know. So the branch diagram, when we have w is equal to f of xy, so we have a function in two variables, and x and y are both given as functions of one variable t, the branch diagram is going to look like this diamond that I have drawn here. So we put our dependent variable at the top of the branch diagram, which is w. We put our intermediate variables at the middle of the branch diagram, and then we put our independent variable or independent variables, depending on how many we have, down at the bottom of the diagram. And between each variable, so we start at the dependent variable and then go down to our first intermediate variable, which would be x. We're going to take the appropriate derivative along that path. So when we go to w, from w to x, we have the partial derivative of w with respect to x. When we go from w to y, we have the partial derivative of w with respect to y. And then when we go from x to t and from y to t, we just have the ordinary derivative, dx dt or dy dt from Calc 1. So we're going to fill in our branch diagram like this. And once we have a branch diagram, then we can get the derivative of w with respect to t by multiplying the derivatives along each path from w to t and summing the products. So let's make that a little bit more explicit. In this case, with our branch diagram, we have the derivative of w with respect to t is equal to, and we're going to start going down the path to the left here. So we have the partial derivative of w with respect to x multiplied by the derivative of x with respect to t. And notice that that's the first product that shows up. And then we're going to sum that product with the products we get when we walk down the other path from w to t. So here we get the partial derivative of w with respect to y times the derivative of y with respect to t, and that'll give us our second product. Okay, so let's move into an example where we are actually going to be using the chain rule. So let's say we have the function w is equal to xy, and we want to find the derivative of w with respect to t along the path x is equal to cosine of t, y is equal to sine of t. So we want to find the derivative of w with respect to t, and then we're also going to evaluate that derivative at t is equal to pi over 2. Okay, so using the theorem from above, we know that the derivative of w with respect to t is going to equal partial w with respect to x times dx dt plus partial w with respect to y times dy dt. And now let's solve for all of these different expressions that are showing up in here, these 4 different expressions. So partial w with respect to x is just going to equal y, because w is just equal to x times y, and in this case we hold y constant. And then we have the partial w with respect to y is equal to x, because x is going to be held constant. And now we evaluate dx dt, and this is just the ordinary derivative of cosine of t, which is equal to minus sine of t, and dy dt is going to equal the ordinary derivative of sine of t with respect to t, and we get a cosine of t there. And now we can just substitute all of these different expressions into the equation for dw dt, and we find that the derivative of w with respect to t is equal to ultimately this cosine squared of t minus sine squared t. One thing to note here is that notice when we first substitute, we still have these lingering y and x variables inside of our expression for the derivative of w with respect to t. What we want to do is substitute for whatever y's and x's we have in that equation. So notice that we substitute y for with sine of t. We substitute x with cosine of t. The reason being that we want to get the derivative of w with respect to t solely in terms of the variable t. So we get it down to cosine squared t minus sine squared t. And now we can evaluate the derivative of w with respect to t at t equals pi over 2. And to do so, we just take the value pi over 2 and plug it into t. And we end up finding that the derivative of w with respect to t at t equals pi over 2 is equal to -1. Now, up until this point, We've been referring specifically to functions of two variables, but we also want to develop a chain rule for functions of three variables. So we're going to move into that for this upcoming section. So we're going to let w equal f of x, y, z be a differentiable function in the variables x, y, z. And we're going to assume that x, y, and z can all be written as differentiable functions in the variable t. And we want to find a chain rule so that we can take the derivative of w with respect to t. And to do that, we're going to use a branch diagram. So again, we're going to take our dependent variable, which in this case is w, and that's going to go to the top of our branch diagram up here. We take our intermediate variables, so the variables giving the function related to w. So we have x, y, and z here as our intermediate variables. And then again, we only have one independent variable here because x, y, and z are all defined in terms of t. And again, we're going to fill in each of the paths between the variables with the appropriate derivatives. We have partial w with respect to x, with respect to y, with respect to z. And then we also have the ordinary derivatives of x, y, and z with respect to t. And again, the derivative of w with respect to t is going to be what we get when we multiply the derivatives along each path from w to t and then add the products together. So let's do that. So the derivative of w with respect to t is going to be partial w with respect to x multiplied by the derivative of x with respect to t. That's our first path. Plus the partial derivative of w with respect to y multiplied by the derivative of y with respect to t. That's the second path. And then finally, plus the partial derivative of w with respect to z times the derivative of z with respect to t. That's our last path, and that'll give us the expression here for the derivative of w with respect to t. So that's going to be our chain rule for functions of three variables. And I give that as a theorem here, but we don't need to go through it because we just developed that theorem. So let's move right on to an example. So in this example, we want to find the derivative of w with respect to t if w is equal to xy plus z, x is equal to cosine of t, y is equal to sine of t, and z is equal to t. So you can see here that our variables x, y, and z are all given as functions of the independent variable t. So by the theorem that we just developed, the derivative of w with respect to t is going to equal partial w with respect to x times dx dt plus partial w with respect to y times dy dt plus partial w with respect to z times dz dt. And we're going to solve for all of these different expressions that are showing up here. So first, partial w with respect to x. Well, y and z will be held constant. And ultimately that gives us a y. Partial w with respect to y, we have x and z being held constant, and that'll give us an x. And then the partial derivative of w with respect to z is going to give us a 1, since x times y is just a constant. Also, we have dx dt is just the derivative of cosine of t with respect to t, and we get a minus sine of t. We get dy dt is equal to cosine t, since it's just the derivative of sine of t. And then finally, dz dt is going to equal 1, since it's just the derivative of t with respect to t. And now we can take these different expressions and plug them in. So we find that the derivative of w with respect to t is equal to y, which is the partial w with respect to x, times the derivative of x with respect to t gives us this negative sine t, plus x times cosine of t plus 1. And if you want to just verify where all of those different values are coming from, then just pause the video and look up above at the partial derivatives and the ordinary derivatives that we just calculated. And after that, again, we don't want these y's and x's appearing inside of our expression for the derivative. So we're going to substitute y and x for the appropriate expression with respect to t. So x will be substituted with cosine of t, y will be substituted with sine of t, and we end up with a minus sine squared t plus cosine squared t plus 1, and that's going to be our derivative of w with respect to t. And we can also evaluate this derivative at the point t equals 0, and to do so we just take 0 and plug it in for t, and in that case we get the value 2. So again, the process for functions of 3 variables is very similar to the process for functions of 2 variables. Just remember to use a branch diagram in order to get what the chain rule is going to look like for your specific function. And now notice that x equals cosine of t, y equals sine of t, z equals t gives us a parametrization of a curve in space. So this is how we define the variables x, y, and z in terms of the variable t from the example before. And remember from previous chapters that this was the parameterization of what's called a helix in space. It looks, let's see if I can kind of draw this. That's really bad. I'll try again. See if I can kind of draw this so that you get an idea. So a helix is going to be a spiral that goes up the z-axis, kind of like that. That's good enough. And pictorially, or graphically, what this derivative of w with respect to t actually means is that as we are traversing this function, or the graph of this function, f of xy is equal to w, we're traversing that function along this line here. And as we are traversing along the line, the derivative of w with respect to t is giving us the change in our vertical component. So this is our vertical component here. It's giving us the change in the vertical component with respect to time as we are tracing out this helix here. So that would be a pictorial representation of what's going on that hopefully gives you an idea of why we would be interested in finding ways to calculate the derivative of w with respect to t. It's because it allows us to give a description of the rate of change of the variable w with respect to time as we're walking along or tracing out a curve in space. So that's the idea. From here, we want to move on to a third type of function. So we're going to talk about functions defined on surfaces. And hopefully you can see quickly the difference between these functions and the functions we had talked about before. So for the preceding functions, w equals f of x, y, z was given as a function of 2 or 3 variables. Whether it was 2 or 3 was kind of irrelevant, but each variable was given as a function of one independent variable t. So we would write x as a function of t, say g of t, and y was a function of t, and even z was just a function of t. In this section, we want to talk about functions where our intermediate variables x, y, or z are written as functions of more than one independent variable. So they're going to be written as functions of 2 independent variables, something like x equals g of rs, y equals h of rs, and z equals k of rs. So what are we going to do for functions where we have 2 independent variables? So if we try and start by making a branch diagram, we run into a little bit of a problem, at least with the knowledge that we have from the previous branch diagrams that we've drawn. So we can still write our dependent variable w at the top. We can write our intermediate variables in the middle, x, y, z. And now we can write our independent variables at the bottom, r and s. But if we try and draw derivatives between each of the points here in our branch diagram, what are we supposed to do when we get down to the intermediate variables going to the independent variables? Because if I wanted to draw a branch going from x down to the independent variables, I have to draw a branch that goes from x to r, as well as a branch from x to s. And so I would have two different derivatives there. And so this is going to present a new kind of issue that has to be resolved with branch diagrams when we have more than one independent variable. So here, well, I should say that we're going to explain how to fix this little problem with branch diagrams below, or maybe I shouldn't even call it a problem, just say account for this additional issue below. But here, w is a function of two variables with respect to r and s. So before we could write w as a function of one variable, just t. But now w is going to be a function of two variables r and s when we compose. So we can only take partial derivatives of w with respect to r and s. It wouldn't make any sense to take just an ordinary derivative of w with respect to r or an ordinary derivative of w with respect to s, because w is now going to be a function of two variables in r and s when we compose, if we're going to view w as that composed function. But what are these partial derivatives going to look like? And this is where we can go back to the branch diagram and make more explicit what we're going to do in this case. So because we have two different independent variables, we're going to split our diagram into two branch diagrams. So we have the branch diagram over here, which is going to be associated to the independent variable r, and we have the branch diagram over here, which will be associated to the independent variable s. And now we have branch diagrams that we should be comfortable with. So again, we have our dependent variables at the top of the diagrams. We have our intermediate variables, x, y, z, in the middle, and then the independent variable. And now we only have one independent variable per diagram, and it's going to show up at the bottom of our branch diagram. And now we can write in the derivatives that connect the different line segments in our branch diagram. So if you look at the diagram on the left here with respect to the independent variable r, we have the partial derivative of w with respect to x right here. And then notice here that it's now going to be a partial derivative of x with respect to r. That's connecting x and r. The reason being that x is a function of two variables. So again, it doesn't make sense to talk about the ordinary derivative of x with respect to r, because x is a function of both the variable r and the variable s. And a similar thing will happen for the branch diagram corresponding to the independent variable s. We have partial w with respect to x, and then now down here we have partial x with respect to s. And the same or analogous things will happen with the variables y and z and the derivatives that are connecting the different variables. And in this case, we have the partial derivative of w with respect to r is equal to the product of the different derivatives showing up along each path from w down to r, and then those products added together. So this should be similar to what we did with branch diagrams from before. So we have partial w with respect to z times partial z with respect to r. That's going along this path over here, plus partial w with respect to y times partial y with respect to r. That's going down the middle path, plus partial w with respect to x times partial x with respect to r. That's going down the leftmost path in our left diagram here. And that'll give us the partial derivative of w with respect to r. And I'm not going to go through the partial derivative of w with respect to s, because it is exactly what you would expect it to be at this point. And again, I list this as a theorem here inside of this box, but that's really just for quick reference for you, because the theorem just states exactly what we just discovered from looking at the branch diagram. So let's move down to an example. So say that we have the function w is equal to x plus 2y plus z squared, and we also have that x is equal to r divided by s, y is equal to r squared plus the natural log of s, and z is equal to 2r. So notice that x, y, and z are given as functions of two variables r and s here. And we want to find the partial derivative of w with respect to r and the partial derivative of w with respect to s. So we're going to use the theorem from above for both partial derivatives here. The partial derivative of w with respect to r is equal to partial w with respect to x times partial x with respect to r, and so on through this expression here. I think that's going to get tiresome to say after a while, so I'm going to leave it at that for now. But we are going to go through and calculate all of these different partial derivatives that show up in the expression. So we start out with the partial derivative of w with respect to x, and we find that it's equal to 1. We then get the partial derivative of w with respect to y, and that's equal to 2. And then we find the partial derivative of w with respect to z, and that's equal to 2z. Again, if you want to, you can stop the video here and just make sure that all of those calculations are correct. And we also have that the partial derivative of x with respect to r is equal to 1 over s, and then partial y with respect to r is 2r, and partial z with respect to r is just 2. And once we have all of those values, then we can plug back into our expression for the partial derivative of w with respect to r, and we get 1 times 1 over s plus 2 times 2r plus 2z times 2. We can make that look a little bit nicer here by making it 1 over s plus 4 times r plus 4 times z. And again, we don't want these intermediate variables showing up in our expression here for the partial derivative. So we go back up and look at z in terms of the variables s and r. We find that z is just equal to 2 times r. So we substitute 2 times r for z. And then ultimately this gives us 1 over s plus 12r. And now we can move down to the partial derivative of w with respect to s. And the process is going to be basically identical here. So again, we just use the theorem from above. This is our expression giving us the partial derivative of w with respect to s. And we work on finding values for each of those partial derivatives. We already have partial w with respect to x, y, and z from the part above. So we're really only worried about partial x with respect to s, partial y with respect to s, and partial z with respect to s. And you can take my word for it that in this case we get negative r over s squared, 1 over s, and then 0. And now we're going to take all of those different expressions and plug them back into our expression for the partial derivative of w with respect to s. And we ultimately get minus r over s squared plus 2 over s. And in this case, we don't have any intermediate variables to substitute for, so we can just circle our answer there. It is 2 divided by s minus r over s squared. Okay, and let's move on to another example here. The importance of this example, the reason that I included it is because here we have w is a function of two variables here, just two intermediate variables, x and y, but x is a function of two variables and y is a function of two variables. So here we're going to be exploring what happens when you have a function of two intermediate variables where each of the intermediate variables is given as a function of two independent variables, whereas before we had three intermediate variables. So again, it's probably exactly what you would expect is what happens. So when we take the partial derivative of w with respect to r, we just get rid of the third component that was there from before. So before we had to add the partial derivative of w with respect to z times the partial derivative of z with respect to r, but in this case we don't have an intermediate variable z, so nothing goes right here, and we just take these the first two paths, I guess, if you were drawing a branch diagram. And I guess other than that, I don't even really feel the need to go through this example. The point of the example was just to express what happens when you only have 2 intermediate variables as opposed to 3. So if you are interested in going through the example, then you can either stop the video, read through it, make sure you understand what's going on, or you can just look at the lecture notes later that I post to Blackboard. Either one would be fine. All right, now the last order of business for this video is to talk about how the chain rules that we have developed above give us a trick for implicit differentiation. So let's develop this trick, prove why it is the case. So suppose that we have a function big F of xy and that function is differentiable, and also suppose that this function f of xy being set equal to 0 defines y implicitly as a differentiable function of x. So what exactly do I mean by that? I mean that you have a function f of xy, let's say it looks something like x squared plus y squared. That would be a function in the variables x and y. And I'm saying that when you set that equal to 0, so x squared plus y squared is equal to 0, this is actually defining a function y in terms of x that you would get by solving for y here. So y squared is equal to minus x squared. You could take the square root, and then you kind of get a function for y in terms of x. That's all I mean when I say that setting the function equal to 0 defines y implicitly as a differentiable function of x. So when this is the case, then we can let w equal f of xy, and then we can examine the derivative of w with respect to x. Why can we do that? Because if we specify that f of xy is equal to 0, then y is an intermediate variable that's being given as a function of x, and of course x is a function of x. And so in this case, the only independent variable we have is x, and we can set up a branch diagram that gives us the derivative of w with respect to x. So w is our sole dependent variable at the top. We have x and y as intermediate variables, and then x as the only independent variable at the bottom. Notice that we do kind of have this weird derivative of x with respect to x that's showing up here, but it won't cause any problems. It'll actually simplify nicely. So then, the derivative of w with respect to x is equal to partial w with respect to x times dx dx plus partial w with respect to y times dy dx. And since we've said that w is equal to f of xy is equal to 0, so we've assumed that w is equal to 0, then the derivative of w with respect to x is also going to have to equal 0. And so we can take this equation up here and rewrite 0 is equal to partial w with respect to x dx dx plus partial w with respect to y dy dx. And we also know that the derivative of x with respect to x is just equal to 1. So again, we can simplify that expression down to 0 is equal to partial w with respect to x plus partial w with respect to y times dy dx. And now once we get to this point, we can solve for dy dx. And we find that dy dx is equal to minus the partial derivative of w with respect to x divided by the partial derivative of w with respect to y. And I list that fact in the theorem here. So if we have that function f of xy and it's differentiable, and the equation f of xy is equal to 0 defines y as a differentiable function of x, then as long as the partial derivative of f with respect to y is not equal to 0, dy dx is going to equal the negative partial derivative of f with respect to x over the partial derivative of f with respect to y. And let's move right into an example where we apply this theorem. So let's say we have this equation here, y squared minus x squared minus sine of xy is equal to 0. and we want to find dy dx given that equation. So in this case, our big F of xy is going to equal the left-hand side of that equation. So the y squared minus x squared minus sine of xy. And notice that this is just a function in the variables x and y. And we can apply the theorem from above. So in this case, dy dx is going to equal negative f sub x divided by f sub y. So the partial derivative of f with respect to x, again, we just hold y constant and then take the derivative. We get that it's equal to minus 2x minus cosine of xy times y. And so the minus f sub x is going to equal 2x plus y times cosine of xy. Similarly, we can take the partial derivative of f with respect to y. So we just hold x constant and take the derivative, and we get 2y minus x times cosine of xy. And by the theorem from above, this implies that the derivative of y with respect to x is equal to 2x plus y times cosine of xy over 2y minus x times cosine of xy. And so you can see the power of this theorem here. If I gave you the same problem without the theorem and said solve for dy dx, the algebra there is going to take you quite a bit longer. And so it's nicer to use this theorem from above and write down dy dx relatively quickly. And now for three variables, we can generalize this result. So if we have three different variables, x, y, and z, then partial z with respect to x is going to be negative partial derivative of f with respect to x divided by the partial derivative of f with respect to z. And the partial derivative of z with respect to y is going to be negative f sub y divided by f sub z. And again, let's do an example here. So we want to find the partial derivative of z with respect to x and the partial derivative of z with respect to y at the point 0, 0, 0, so at the origin, if we have x cubed plus z squared plus y times e to the xz plus z times cosine of y is equal to 0. So again, notice that we have three different variables defining or giving us the left-hand side of this equation here. So in this case, we have a function big F of x, y, z is equal to the left-hand side of our equation. And again, that's going to be set equal to 0. So we can use the theorem right here from above. So the partial derivative of z with respect to x is equal to minus f sub x over f sub z. So let's find f sub x first. To do that, we take the derivative letting y and z be constant, and we find that it is equal to 3x squared plus z times y times e to the xz, and minus f sub x is going to be minus 3x squared minus z times y e to the xz. Similarly, we can find the partial derivative of f with respect to z by holding x and y constant, and we get 2z plus y times x times e to the xz plus cosine of y. And after we have these two expressions here for the partial derivative with respect to x and z, we can just write down that the partial derivative of z with respect to x is equal to this expression here, this minus 3x squared minus z times y times e to the xz over all the stuff that I have written here on the denominator, or in the denominator, which I don't want to say again. And now we can look for the partial derivative of z with respect to y. And again, by the theorem, we know this is equal to minus f sub y over f sub z. So f sub y is equal to e to the xz minus z times sine of y, where again, to find this partial derivative, we just let x and z be constant and take the derivative. And this gives us that minus f sub y is equal to minus e to the xz plus z times sine of y. And f sub z we already have from the first part where we solve for the partial derivative with respect to x, so we can just keep that the same. And we find that the partial derivative of z with respect to y is equal to z times sine of y minus e to the xz all over the expression that we already had for f sub z. And again, if you didn't see it from the first example, then hopefully you can see here how powerful this theorem is, because it saved us from doing a lot of algebra solving for these partial derivatives using implicit differentiation. All right, so that's the end of the material for section 14.4. I think that it's relatively straightforward material, but it will take some practice. I'm going to give out some homework for 14.4, so hopefully you can practice drawing branch diagrams and then taking derivatives using the chain rule for all kinds of different functions with different intermediate variables and independent variables and such. And other than that, just look forward to the next video on section 14.5.